Welcome to AI for Good, the leading, action-oriented, global and inclusive United Nations platform on AI. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with 40+ UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to identify innovative applications, build skills and standards, and advance partnerships to solve global challenges. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Thank you, Anna, for introducing the session. A very good day to everyone, and thank you for joining. Welcome to AI for Good's AI and Machine Learning 5G webinar. My name is Jiaying Meng from ITU, the International Telecommunication Union. Today, we have a very interesting talk titled Estimation of Site-Specific Radio Propagation Loss with Minimum Information. This talk serves as an introductory webinar to the related challenge, which aims to estimate the radio propagation loss with limited data without compromising the general results of the estimation. In this webinar, our speaker will explain the tasks to be accomplished by the participants, evaluation methods, logistical details, and the prizes for the winners. But before officially kicking off the session, I would like to introduce our esteemed speaker, Kazuki Takezawa-san. Takezawa-san is a researcher at KDDI Research with a specific focus on radio propagation models for outdoor environments using AI and machine learning and simulations of radio propagation between satellites and the ground. And my colleague Vishnu, who will be taking care of the Q&A session. Now, without further ado, I would like to pass the baton to Takezawa-san. Takezawa-san, the floor is yours.
Thank you for the introduction. Now I will share the screen, so please wait a moment. Okay, is it okay? Can you see it?
Yes, we can see your screen.
Thank you. Thank you. So I will explain the challenge problem, estimation of site-specific radio propagation loss with minimal information. So I'll explain about the first background. For stable mobile communication, understanding site-specific radio wave propagation characteristic is essential. In particular, the location of base station that transmit radio waves needs to be decided based on understanding of propagation loss, which varies due to reflection from surrounding buildings and diffraction around obstacles. This is especially significant at high frequencies such as FR2 or FR3, or we say 28 GHz or 7 GHz. The propagation loss tends to fluctuate greatly depending on the environment. When the base station has a line of sight or just a LOS loss to a device, such as a smartphone, the propagation loss mainly depends on distance. However, in non-line of sight conditions, where the signal cannot directly reach the device, the radio waves arrive through reflections and diffraction from buildings, making it crucial to understand these effects. So next, regarding estimation of site-specific radio propagation with AI/ML, measuring propagation loss directly is one way to understand it, but doing measurement at various transmitting and receiving points involves significant time, effort, and cost. Therefore, estimation methods used AI/ML are expected to be effective. For example, if propagation loss measurement data are used as training data, and environmental information such as building layouts and terrain elevation are used as parameters, and AI model can accurately estimate losses without extensive measurements, saving time and resources. Then another key point is the selection of the transmitting and receiving points for training, how to select them effectively. So next, the objective and approach of this challenge program. The objective is to build generalizable AI model for propagation loss using as little data as possible. Reduction the amount of data required for training also lowers measurement costs. Furthermore, creating a versatile AI model allows us to understand propagation losses at various transmitting and receiving locations under different conditions. Then regarding the approach, you may freely consider different estimation methods, such as which measurement data should be used, what parameters should be employed, and what kind of model should be developed. For instance, a physical propagation-based approach might use environmental information like building layouts and antenna height for analysis, while a data-driven approach might ignore physical propagation details altogether. And other approaches are also allowed. The task for this challenge, there are two tasks. Task 1 involves estimating propagation loss over the entire area using data from a few receiving points. Then task 2 involves estimating the data from a few transmitting points. You participants should consider either one or both tasks. In task 1, reduce the amount of receiving data, preferably with minimal information about transmitting locations. And similarly, in task 2, aim to reduce the amount of transmitting data and also keep the number of receiving locations and propagation loss data as small as possible. Design AI models that correspond to each task. Considering data reduction strategies, different methods can be applied to each task if preferred. Then next, about the datasets to be distributed. There are two datasets, 3D map data and propagation loss data. The 3D map data are in OBJ format, representing the Ginza area in Tokyo. The propagation loss data include measurements at 20 transmitting points at frequencies of 28 GHz, 7 GHz, and 800 MHz. These datasets are explained later in the reference section in this document. Next, the model evaluation procedure. First, consider and select a method, then choose training data from the dataset and train an AI model. The target output is propagation loss again. The number of training samples can be flexible, but smaller is preferable. And make sure not to use evaluation data for training. This is prohibited. Using the train AI model, estimate propagation loss for all receiving locations within the evaluation data, focusing on the 5 transmitting points provided. And finally, calculate the root mean square error, or just RMSE, for all transmitting receiving pairs in the evaluation data, as shown below. Then model evaluation conditions. Again, evaluation data must not be used for training, only for testing. Use the provided 3D map and propagation loss data for evaluation. The goal is to assess the accuracy of models developed from a specific dataset. Then additional radio propagation data from ray tracing or FDTD, such kind of simulation, are not allowed. All provided propagation data for training can be used, including data at different frequencies other than the target frequencies. In addition, the use of datasets not included in the provided dataset, such as image data not related to radio wave propagation, is also permitted. Then model evaluation, sorry. Sorry. Okay, it's okay, sorry. And model evaluation criteria. There are 4 criteria. Flexibility of the modeling method across the different locations and the novelty of the technique will be highly evaluated. The method described at the end of this document is given as an example, just example. But if you use it as it is, points will be deducted. And for data selection methods, approaches that use minimal data for training are preferred, especially if they demonstrate technical innovativity. The model usefulness will be evaluated based on the average and variance of RMSE, as shown in the graph on the right. Methods that balance accuracy and generalization are rated higher. Then finally, the number of tasks submitted and the frequency bands considered will influence overall scoring. More tasks and bands are rewarded. Then hours and incentives, IP rights. Top 3 teams will be honored, and there may be opportunity for co-authored papers with KDDI Research. In addition, we will award a total prize of 3,000 Swiss francs, along with a certificate from ETC and secondary prize of 10,000 yen. And all IP rights will follow ITU policy. If you submit patents for your proposal method, you must handle patent application procedure before submission. And winning teams will be required to disclose your proposal publicly through papers or presentations, etc. And next, submission requirements. Submit a PDF of your presentation and a CSV file of the evaluation data. The presentation should include a cover page, team structure, model description, processing time, data selection method, usefulness of the AI model, and a list of submissions. Processing time is not criterion for evaluation, but please include it as reference information. For the CSV file, please add the estimated propagation loss in the 14th column of the evaluation data. And create one CSV file per frequency, transmitting points, and task. For example, if submitting results for 3 frequencies and 2 tasks, you should submit a total of 30 CSV files. And details of CSV structure are provided later. A submission method, questions, and schedule. Submissions are to be made via the IT website for AIML in 5G Challenge. Registration of your team and your user account is required and may take several days, so early registration is recommended. For inquiry regarding this challenge, please use the contact form provided. Response will be given within approximately 3 working days. The schedule is as follows. First, registration of teams and users by October 8th. Question submitted by October 17th. Submission deadline is November 1st. When the team will be announced around November 21st. And followed by presentation at the TTC workshop on IT webinar. Details of presentation dates will be notified separately, but the TTC workshop will be held around 5th December 5th. So, going to next page, this will be good time to questions. You can ask your question in chat, so please feel free to ask anything. Any question? No yet?
Thank you very much, Takeshima-san. Thank you for the very nice explanation and the problem statement. We will take some questions from the audience now. Meanwhile, maybe some clarification on the propagation-based approach. Propagation-based approach and data-driven approach. I think you have 2 approaches. Yes. So in the propagation-based approach, how do you find the number of data points used? Because in the solution you need to use minimal data. So in both these approaches, can you explain how you measure the number of data points used for evaluating the minimal use of data?
Sorry, please wait a moment. solution. So I'm sorry for waiting. There are no certificate number, but I hope you to consider it as little as possible. Does it make sense?
Okay, yeah, understood. Yeah, so
You're
we use minimal data for both approaches, right?
Yeah.
Okay, understood. Okay. Mm. We can take audience questions. If you have questions, you can ask in the chat, and we will take it here. I think the choice of AI architecture, meanwhile, the choice of AI architecture, you had mentioned the different AI architectures. Is there any particular type of model or tool or model that that you want to use for the participant, or participant can use any type of architecture or tool for the model? Can you please explain?
Thank you. We hope participants consider fluidity, including AI model, parameters, information. Oh, sorry, circumstances, information. Thank you. So, if there are any more questions from participants, can I move into next pages? Next page.
Yes, as of now, I don't see any participant questions. There is no other questions as of now.
Thank you. So I will explain further about data sets to be distributed.
Yes, please.
Yeah. Okay, so the 3D map data are distributed in the OBJ text format with coordinate data recorded in UTM coordinate system. There are many explanations about this OBJ format available online, so please refer to them as needed. And it can be visualized and edited with software such as Blender. But please note that during the import, it is necessary to set forward to Y forward and up to Z up. And propagation loss data are distributed in CSV format with 60 files covering frequencies of 28 gigahertz, 7 gigahertz, and 800 megahertz for 20 transmitting points. Each file contains 13 columns with transmitting coordinate on 3D model, latitude, longitude, and height, receiving coordinate on 3D model, latitude, longitude, and height, and propagation loss. Since the coordinates are in UTM, so geometric calculation between points in meters are possible. So regarding transmitting location, the 5 transmitting points marked with left circle, points 5, 9, 12, 14, and 12, no, sorry, 20, I'm sorry, are used for evaluation, while others are used for training. So this is also a good time to ask question. Before we move on, I will take some question if there are no question yet. Okay. So okay, I will move on to next pages.
Yes, go ahead, please.
Thank you. So from here, I will explain An example of propagation loss estimation method by our company for reference, just a reference. This information is provided as a, again, reference, and participants are expected to consider your own methods for this issue freely. First, background. High precision wireless emulation, that is a simulation of propagation, requires site-specific radio wave propagation models. There are two conventional methods for radio wave propagation modeling. One is a theoretical approach that is reproduce objective in a virtual space and sequentially calculates physical phenomena such as reflection and refraction through simulations. To perform these calculations over a wide area, a vast amount of computational resources is required. The other is an experimental approach that involves statistical analysis and regression based on measurement data. As the number of parameters representing the environment increases, the regression becomes more complex, presenting difficult challenges for modeling. As an evolution of this experimental approach, many studies and proposals have used machine learning-based radio propagation prediction methods. For example, environmental feature data, including building information, are used as input for site-specific models based on maps. A common issue with traditional AI model is that learning models with training data generally require large training datasets. Obtaining radio propagation data through measurements demands significant human resources and time. Therefore, we tackle the challenge of achieving high accuracy estimates with limited training data. In this study, transfer learning was used adapting a model training for one task to another. Transfer learning is expected to improve efficiency, especially for similar tasks, by avoiding training from scratch. We also utilize fine-tuning of the train weights without changing the network architecture. In this approach, the fine-tuning was performed in frequency domain. Pre-training was done with the dataset at different frequencies, reducing the amount of data needed for training at the target frequencies. However, these are similar datasets available for pre-training at those different frequencies. So for this challenge, consider both pre-training data size reduction and transfer learning at different frequencies. The map data around the transmitting and receiving points was used as image data. Additionally, the height of direction of the transmitting antennas, the distance and angular relationship between the transmitting and receiving point, antenna gain, and the free space propagation loss were used as parameters. Here, the free space propagation loss is calculated from distance and frequencies representing attenuation in empty space and allows differences across frequencies to be expressed. For environmental data, a map showing the height of buildings around the transmitting and receiving was used with color coding. Within 200 meters around each point, higher buildings are represented with lighter colors. The next, the evaluation data method. Data were collected via physical surveys in central Tokyo. Frequencies of 800 MHz and 22.1 GHz were used, measured on received power from active base stations. Number of data points 89,000 at 800 MHz and 86,000 at 22.1 GHz. The method involved fine-tuning the model, retraining at 800 MHz, then training with limited data at 2.1 GHz. The result of the study. The left graph shows the relationship between the training data amount with horizontal axis and RMSE with vertical axis. That indicates that less data result in higher LMC. And orange symbols show orange symbol and lines show model pre-trained at 800 MHz and fine-tuned at 2.1 GHz. And gray symbol and line show conventional model without pre-training. It shows limited data causes significant degradation in accuracy with conventional methods, but with our method, accuracy degrades less. And for training also enables faster learning, but details are omitted here as that are not directly related to these challenges. So this concludes the presentation. That's it. Thank you very much.
Well, once again, thank you very much, Takashin-san. The data sets.
Sorry.
Yeah. So the fine-tuning mechanisms and the pre-training mechanisms, are there some specific references or techniques or notebooks that you refer to, or it's up to the participant to decide what type of fine-tuning and what type of pre-training? Are there specific scripts or mechanisms that you provide?
We hope the participants will consider the model and method freely, but if you're interested in this structure and method, please look at these papers. Thank you.
Thank you very much. Participants can also ask questions through the chat window. Meanwhile, I think the relation, you have references to different saving in terms of measurements and prediction of the number of points with estimates, I think. So the minimizing the number of measurements and prediction of large number of points with estimates, this is an important task for the participant. And can you please explain the relationship between accuracy of the collected measurements or the generalization in terms of covering large area? So it is there are two parts. Firstly, the effort required to reduce the effort required for measurement, and secondly, increasing the coverage of the already existing manual measurements. I think there are two parts. Can you explain if the participant looks at both the first case of reducing without compromising on the overall radio propagation estimation, or the improving the accuracy of already collected measurements, please?
Please wait a moment. Thank you for asking. I think we think the balance is important. not just less data and not just variance and not just accuracy. We value the we highly value the balanced method.
I see. Okay, okay. Understood. So it should be a balanced approach. Okay, okay. Mm. The participant has to submit the model weights, or do you need the model weights from the participants?
Sorry, I couldn't get. I couldn't hear what you say.
The model
More
parameters.
than
Yeah. The participant has to submit to you the model parameters, their tuned model parameters.
Yep. Thank you. Yeah. So your participants need to submit the PDF file, and it includes the description, the method. Of course, it includes the parameters.
Okay. Can you again explain the timeline for this challenge? So the
Schedule.
time. Thank you. Okay. Yeah, this is very clear. Yeah. I think we don't have any other questions. I think the presentation is very clear. Problem statement is also very well explained. The registration link is published as well. Thank you for your nice presentations. If there are any other questions, we can take it from the chat. Okay, we don't have any other questions, so we would like to thank the colleagues, and here you can send the questions using this. There is a discussion forum where you can ask questions also, in the Challenge AI for Good website below. And we would like to thank the colleagues for hosting, and we can invite James on to close the session if that's okay.
Thank you, Vishnu, for the Q&A session, and Takezawa-san for your contribution during the whole talk. Now, I would like to thank everyone who participated in this webinar until now, and please note that our challenge is already open and open for registration and participation. The link to the challenge is also posted on the video wall. You can now start working on the solutions and submit the results on the portal. Several prizes and certificates, as explained, are planned to be handed out to the winners of the challenge. Please feel free to participate, and free computes and GPUs will be provided based on needs. We have more sessions in the future. Please check the AI for Good program page for more details. Looking forward to your submission, and thank you for joining. See you next time.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for good.
先生、塚部さん、ありがとうございました。
ありがとうございました。
ありがとうございました。
はい、失礼いたします。はい。